I guess the only announcements I have for today are that I put on the, well, I guess a couple things that I added to the website. One is that on Monday, as I said yesterday, I believe, we're going to do our second round of paradox presentations. So I really want you to think about, first of all, if there's some problem where sharpening your argument about how to make sense of the paradox, that's of foremost importance. But then also making it more digestible. You know, if you had too much mathy stuff in there and that took away from the thrust of the argument, try to pare it down. And if you want to support it with a, an example with real numbers in there, say these things are moving at relative speeds of c over 2, sometimes that's good. You want to choose an example that's as simple as possible, but it sometimes helps if you can just make the resolution of the paradox seem plausible, like I can see a way out without working the numbers through, and then support it with an example with some numbers. But we certainly don't need to see all the calculations of every step of everything. That usually doesn't help. We're willing to take your word for it that you can calculate the length contraction and relativity of simultaneity kind of stuff. But showing that a bunch of numbers add up the way that you're hoping they add up, that's something that, we're willing to take your word on that it actually did work out, rather than showing us all the detailed calculations. The other thing is the chapter 17 homework. I think I first put it on yesterday. Again, it's due Wednesday, so start really digging into that this weekend. It looks really thick, but that's because there's a whole bunch of diagrams with stuff that I copied out of another textbook, where there's not, in most of the problems, there's not that much to do. You just look at the diagram and answer some questions about it, about which things will happen first from someone's point of view or something like that. So don't be daunted by the amount of paper or pages in the PDF that it looks like it takes up. It's just because I included a bunch of bulky diagrams in there, but there's some drawing of your own diagrams, and that's good practice too. Okay, I'm backing up as if I'm ready to start talking about my presentation, but it's not up yet. Any other comments, concerns? I feel like there was one more thing I wanted to talk about. Oh yes, the reading. There's one more chapter that the reading hasn't been assigned for yet, and I decided to make the reading optional for that last chapter. And there's no requirement. In fact, I removed the link for the reading responses for it, so you wouldn't feel obligated. I'm still more than happy to answer any of your questions on that section, but I didn't want you to feel obligated to respond. So that's chapter 18. It's nominally on E equals mc squared and energy and momentum. It just throws out a bunch of concepts that we haven't encountered yet in this course. And I'm going to try to work my way through it next week. So Monday we'll be doing presentations, but probably Tuesday and Thursday. Wednesday's our exam. And I'll have to think about the last round of presentations, whether that's Friday or what. But it will at least have 2 more days of talking about that material. I don't know that that's enough, but we'll see where we get to. So you can look at that reading section. I think last time I assigned it and people thought it was pretty confusing. So I'll work my way through it my own way, and we'll do practice stuff with it in class. Okay, so let me share this. We've been talking about our space-time diagrams, or when you add the structure of how to change those axes as you switch between IRFs, and how they sort of bend and get crushed towards the middle or spread wide apart. That, when we add that structure, we call them Minkowski diagrams. Okay, so that's the subject of this chapter. And there's a lot that Merman does in here, and one of the things he analyzes is how can we understand the length contraction? In other words, what might seem paradoxical early on is that I see your meter stick as being short, you see mine as being short, and that sounds like a paradox, at least in the normal way we speak. So here's a diagram that I've copied out of his. There we go. Copied out of his book. And we've got 2 meter sticks, and they're passing by each other. Again, the context is we're pretending our whole world is just the x-axis. So you can either think of 2 people are holding meter sticks and they can pass right through each other on this one-dimensional world, or maybe they're just moving right next to each other and we're just going to plot their x coordinate, right? They're moving along the x-axis, but they don't have to actually pass through each other, but they're just adjacent to each other. And all the movement and the length of the sticks is all along the x direction. So in one frame, I'll call that F here, 1 meter stick, it's 100 centimeters long, so here's x in centimeters. I'm showing that meter stick in red, and its world sheet is this vertical sheet shown going straight up with one edge going there and the other edge going there. So that's the world sheet of that meter stick viewed from the IRF in which it's at rest, right? Those are the ones with the horizontal and vertical axes. And then there's another meter stick which is moving in that IRF, and that's the one where the left edge of the meter stick is here and the right edge of the meter stick is here. That's the world sheet of the one that's moving. And we can see that it's moving because its left edge is getting to a larger and larger x coordinate as time increases, and so on, right? And Merman's put our scale markings on here with the scale factor, so you can see the distance between 40 and 60 is bigger than it is down here. It's been rescaled. And the question is, how is it that these 2 meter sticks, we can see here that they're both 100 centimeters in their own rest frame, right? The rest frame of this one is the horizontal and vertical axes. What we do is look at a particular time, in other words, on the x-axis, what extent this world sheet takes up as we slice through with the x-axis. It's 100 centimeters. What about this world sheet as viewed from its rest frame? Well, its rest frame's x prime axis is here, and it goes exactly 100 centimeters to slice through it. That's at a particular time. This is all the locations taken up by the meter sticks, and it's 100 centimeters too. So in their own rest frames, they're 100 centimeters each. But they're not 100 centimeters when measured from the other rest frame. In other words, if I cut through this tilted world sheet with a horizontal x-axis, in other words, I ask, how long is the moving meter stick when it's cut through at a particular time? It's only 80 centimeters long. Okay. What about the same kind of comparison in the other frame? Well, here's the green meter stick. It's at rest in that particular frame. And then this one that's going straight up and down in the diagram is moving with respect to the tilted axis frame. And if we want to figure out how long this, rectangular kind of world sheet is in that frame, what we do is slice through it with the x prime axis. Okay, so I take a slice through it, and it only slices through it up to 80 centimeters. So each of the meter sticks is 100 centimeters long in its rest frame, and measured to be 80 centimeters long from the frame in which it's moving. Questions on that kind of construction? So that's how you can see the length contraction directly in the Minkowski diagrams. We've done lots of calculations, but this is a visual way to envision it. It seems impossible, but it has to do with the tilted axes and the scale factor. All of that comes into it crucially. Here's the next thing Merman tries to sort of show that is encoded in these diagrams. How can F and F prime each see the other's meter clock? That was an editing mistake there. Each one sees the other's clock as moving more slowly or ticking more slowly. So let's imagine, again, we're going to have F being the one with the horizontal and vertical, X and CT axes, right? And here is one tick of a clock that's sitting at rest in that frame. So it happens to be at the origin, right? And it's ticking. Maybe these are 1 second ticks. Merman plots T instead of CT, but that's okay. We won't be too confused about that. It's just time varying as you go up. So each one of those intervals is a 1 second tick. Now let's imagine a different frame that's moving. So it's got a tilted T prime axis over there, and there's a clock that's at rest in that frame. And of course, it's ticking. but the distance on the page that each of these ticks takes up is different than the distance on the page for each one of these. We got to use the scale factor to translate between them. Okay, and the question Merman wants to ask is, how does one see the other one's clock as running slowly, and would the other see one's clock as running slowly? Okay, it's a little bit hard to read here. I know the text on here for those in the classroom is kind of small. This says t equals 5 seconds. Okay, so 5 seconds has elapsed since t equals 0 when the two origins passed each other of the coordinate systems. And this is what's happening at t equals 5 seconds. And if we want to know the reading on the clock that's moving in that frame, when the time in this frame is 5 seconds, its reading is exactly 4 seconds. So we would say, you know, they both agreed, they both read 0 when they were passing by each other, and one's only ticked off 4 seconds, the other one's ticked off 5 seconds. The moving one, from this frame's point of view, is ticking slowly. What about from the other point of view? Well, remember, a line of constant time, a particular time, just like we did with this blue one here. How do we draw a line of constant time in a certain frame? We draw it parallel to that frame's x-axis. So here, if we want to consider the moving frame's point of view, here's its x prime axis. This is a line of constant time from that frame's point of view. This is a line of constant time from that frame's point of view, right? So this event right here, this clock that's in frame F, at rest in frame F, reads 4, is simultaneous with this moving clock, which is at rest in the F prime frame, reading 5. So when they read 5, they assess at the same time according to their sense of what the same time means, their sense of simultaneity, that the clock in the F frame reads less time. So it's ticking slowly. Right? We've ticked off more, so theirs ticks off less time. Their ticks are taking longer, and we would say the clock is running slowly. So that's the time dilation shown in these diagrams. And Merman, I'm not going to go into more details here because we could, spend a lot of time talking about this. He also derives the formula for the lagging clock leads by LV over C squared and derives the Lorentz transformations from these diagrams, but you can read about that if you really want the details. Everything we've talked about is encoded in these diagrams in sort of a visual way. It's not the most intuitive way you're used to working with space and time, but that's the whole point of this course. We're trying to develop a new intuition, a new apparatus to work with it. Okay, here's just to hit a few reading responses that were posted on chapter 17. I did like all the images used, though, especially the ones that showed a full grid which had been distorted. I'd have to look at that. I think the grid has been turned into like parallelograms. Probably it was a square grid, but in the other frame, the square grid becomes a parallelogram kind of shaped grid. It's interesting to see a visualization of this bending space-time that we've talked about. The reason I put this up here is because this is one of the cases. Everything in this chapter is not having to do with bending space-time. This is what we call flat space-time. This Minkowski diagram, this two-dimensional diagram, doesn't have any bubbles coming up out of the page or any of that kind of stuff. So we are visualizing, even though that grid got distorted, it's still a way of laying some coordinates on flat space-time. So when we're talking about curved space-time like we did a while back, what we're seeing in chapter 17 has nothing to do with that. Despite the fact that the coordinate systems are a little bit wonky, the space-time itself is still flat. Remember, when we look at the space-time that underlies all these coordinate systems, it's just a regular flat plane, right? The collection of events we just envision as a flat plane that way. My biggest lingering question is why exactly the primed axis form a smaller area angle than the regular right angle that the normal axis makes. Yeah, it's sort of strange that, when one frame is moving very quickly to the right with respect to another frame, the x prime and the t prime axes are almost in the same direction. They squeeze together, and that means the area that's between the x prime and the t prime axis seems like it's not as much. And that just has to do with that distances and times between assessments between frames are not the same. In other words, if I measure a certain distance between events, you moving relative to me in a different IRF are going to measure a different distance. And the same thing for between events. And so we shouldn't expect a square area, which has a side which is a difference between times, and another side which is a distance between events. When it's translated into the other frame, is going to preserve its area because the lengths of the sides aren't even going to be the same. But it turns out it's not even perpendicular anymore. I wonder, how could Minkowski diagrams and Minkowski space be helpful in solving problems? Well, they're not so helpful if you want a very precise answer, because we're measuring things with rulers and constructing with protractors and so on. But they are helpful for making things that seem counterintuitive at least more visualizable. And that's what's going on in the remainder of this chapter. And I'll probably elaborate a bit more. Now, I can't remember if this discussion of the twin paradox, if I've taken this from chapter 16 or if he revisits it in chapter 17. It must be in chapter 17 because we're doing a Minkowski diagram. Chapter 16's subject was the twin paradox. And chapter 17, I think it's revisited from a graphical point of view. It really is helpful. So let's remind ourselves of the situation. Here we are taking the x and ct axes to be horizontal and vertical in the rest frame of Earth. So Earth is just sitting here, right? It's going up like this. Its world line is vertical. And then we've got a traveler, so the speed of light something's moving at the speed of light would be going along this dashed line, world line of photons leaving Earth with the traveling rocket. And there's a rocket that's traveling very close to C. It goes out to the location, in my version, I would say here's planet X's world line. It's at rest with respect to Earth, till they hit planet X. And maybe this is a shuttle that keeps going, but they drop off the people at planet X, or they drop them off on this incoming shuttle, and then the traveler Stella comes back at the same rate, but in the opposite direction. And you can see, because of the high speed, the distance between these tick marks is much smaller than the distance between these tick marks. The scale factor gets quite large when V is close to C. So Merman's trying to make a big difference happen here. Okay, let's label some events in here. Event 1 is the spaceship leaves Earth. Everybody can see that. Event 2 is, you could either say the travelers arrive at X or leave X, or they switch from one shuttle to the other. In any case, those are all publicly identifiable events, so everybody can talk about them in an unambiguous way. And the question is here, how long did it take between event 1 and event 2? Well, Earth says that's 5 years. These are marked in years right here. So it took 5 years to get there, right? The t coordinate of E2 is 5 years. Whereas F prime, the frame that's moving along with the outgoing shuttle, there's only 3 years that tick off there. Okay? And similarly, there's 3 years that tick off going back. So it takes 6 years versus the full 10 years as assessed by the Earth. Okay. Now, it's tempting to think that a particular coordinate here should have a certain time assigned to it, right? We're used to thinking like Newton and say, well, if the Earthlings think that 5 years have elapsed, so should people on the ship. But that's Newtonian thinking. In reality, every object that's winding its way through space-time is going to assign its own time coordinates to events in different ways, right? So here we're comparing one that happened to sit still, at least as seen from the Earth frame, and one that happened to move uniformly. But there would be a different case if somebody, went slowly at first, and then they went quickly, and then they went slowly, and then they went quickly. They would get a different time coordinate. How much time has elapsed between when they left Earth and when they arrived at the rendezvous point out there at planet X. Okay. Now, let's get back to this question, which, again, is going to be somewhat addressed, I think, by the group who's presenting on the twin paradox. You can go so deep into this twin paradox. But the fundamental question I raised way back when is, well, the question is, when you arrive here at X, what's going on at the same time as Earth? Because we seem to see a big gap in time, if you remember the analysis. I'm really tempted to ask the question, when I'm here, what's going on back at Earth? And the answer depends on which reference frame you ask it from. Even though I'm located here, I might be passing by in the outgoing reference frame or the incoming reference frame or one that's just sitting still on X or anything in between there. So let's first look at the reference frames corresponding to the outgoing and the incoming shuttle. So the outgoing shuttle, that's the one moving along here, its X prime axis looks like this. You can barely see it here in the classroom, but it's a red line going there. That's its X prime axis. So that's a line of constant time for that frame. And so that means if I want to know, if I'm here and moving along with the outgoing shuttle, this is a line of constant time. And so the answer to what's going on back on Earth, according to that definition of simultaneity, is, well, whatever's happening 1.8 years after the launch. Okay, for the incoming shuttle, the one whose time axis looks like this, its x-axis is, sort of close, but tilted a little bit with respect to it. So that's what the x prime axis for the incoming shuttle looks like. Here's another line that's parallel to that x prime axis, or we might call it x double prime because we have 3 frames here. So the answer to what's going on Earth at the same time as this event is, well, here's something that's at Earth and simultaneous according to that frame. There's a widely different view of what's going on simultaneously. And you remember the idea, which I think is a good way to visualize it. If I'm asking what's going on in a different galaxy far, far away, I get different answers as I walk towards the galaxy and away from it, right? Something that inevitably happens now happens in the future, and now it happens in the past, and now it happens in the future. And that seems kind of ridiculous when we do it that way. I mean, it either happened or it didn't. Well, no, when you're far away, there's no way to know whether it happened or not. And this notion of what is, what a line of simultaneity is in some sense a construction. And it's the best construction we can make to answer the question from a particular frame's point of view, what's going on at the same time. It's the only reasonable definition, but it's still a definition. And when you think of it in terms of that, it can seem kind of ridiculous. Okay, so there are 2 different points of view for what's going on at Earth, and in reality, you could move it lots of different ways when you're at X and get different ideas of what's going on at Earth at that moment while you're moving that way, right? Any of these different times could be what the current time is, just depending on how I'm moving in the vicinity of that event. Somewhat ridiculous. Okay, now just because we say those words doesn't mean that you're necessarily satisfied with that. I mean, I've essentially said, well, it reduces to a definition. That definition is the best we can do, but it's a little bit uninformative because there's no definite answer to the question we posed. So here's one way you might try to sharpen it up. Let's imagine, so I'm imagining we're traveling from Earth to X, and I'm going to imagine that we have a rigid rod. Now, we already know to be a little bit suspicious about rigid objects from the talk we had about the scissors, and we'll hear more about that next week. A rigid rod which spans the distance between Earth and X. Okay, so we're going to imagine we build this rigid rod. It's made out of the most solid material we can make, and it spans the distance between Earth and X, and it's being held always between, well, it's going to be attached to the rocket, and it has that length. So at the moment when the rocket reaches X, this rod, the distance from Earth to X. If we attach someone to that rod, we can say, well, look down at Earth now. Tell me what's going on Earth. That's going to tell us by definition, right? I've sort of attached someone rigidly to the rocket. Okay, so the idea is this rocket that's going out, we're going to have a rod that's moving with it, and right at the end, we can have someone riding on the end of the rod that's trailing behind the rocket, and at the instant when the rocket passes X, the other end of the rod is going to be right at Earth, and we can have someone riding along with it and tell us what's going on right then, okay? So the question is, what's happening on Earth at the time of turnaround? We've got this rigid rod, that's what it looks like, and we're going to say that by definition, because when we say the rigid rod turns around simultaneously, we know to be suspicious of that. Simultaneously, according to whom? And the to whom is over here. let's say by definition that if you're in the Earth X IRF, you see this rod, every point on the rod switch directions simultaneously. So it was going to the right, and all of a sudden, just from your point of view, it's going to the left. Okay, so what would, if we drew the world sheet of that rigid rod as it's going out and as it's coming back, what would it look like? It would look something like this. Isn't it true that from the Earth's point of view, oops, getting too far away. From the Earth's point of view, this is a constant time, and at that time, every point on the rod switched directions simultaneously, right? And in the Earth frame, at every instant in time, the rod is exactly the same length as the Earth X distance. We've designed it that way, almost by definition. Okay. Now, let's ask if this is, so we're just going to take for granted that we designed an experiment like this, and this is what they see, right? Rigid rod, people on Earth see the rod going out right at the moment of turnaround, according to Earthlings. That's what we mean by the moment. It spans the distance from Earth to X, and then it starts going back. That's what's seen by Earthlings. Now, what would people in the outgoing reference frame, the outgoing shuttle IRF, assess to happen with the rigid rod? Well, this blue line I've drawn here is their X prime axis, so that's a line of constant time. So this is not a line of constant time right here. That's a line of constant time for Earthlings, but not for the outgoing shuttle. For the outgoing shuttle, lines of constant time are parallel to that blue line there. So let's draw a few more lines of constant time and ask ourselves, in what order, according to the outgoing shuttle, did the ends of the rod turn around? Did they turn around simultaneously? Well, we know that's probably not true because events that are simultaneous in one frame, the Earth frame, are not simultaneous in the other frame, the outgoing IRF. Which event happens first, the right end or the left end of the rod turning around according to the outgoing shuttle frame? I can feel I've been talking for too long because, you know, everyone's gotten used to not speaking. How do we figure out in this frame where all these blue lines shown here are lines of constant time, is this line of constant time before or after this line of constant time? In other words, this is a view of what space is according to the outgoing shuttle. This is another view of it at a different time. Which time happens first? The one that's to the right or the one that's to the left? Which of those visions of space is one that's earlier in time according to the outgoing shuttle? Yeah, the one to the right. We have to look at its time axis, right? I mean, we can just see at that, if you want to know when something happened, you follow the space axis until you hit the time axis. So this particular line of constant time, as assessed by the outgoing shuttle, crosses its time axis at, well, it looks like 1, 2, 3 years out, right? Whereas this one, well, you can't see it because it would be off the diagram, but it's eventually, if we continue it up here, it's going to cross this time axis, right? There, slowly, this line that the rocket is on there is going to get closer and closer to this blue line over here, and they're going to cross somewhere way up, probably off the screen. And so it's going to be much more than 3 years. So what that means is this supposedly rigid rod, according to the people who are in an IRF that's heading away from Earth and toward X, that, you know, this is their time axis, the right end of the rod turns around first. In other words, the event corresponding to the right end of the rod changing directions happens first. Left end of the rod changes directions quite a bit later. Now, what does that mean when we're calling this a rigid rod? Certainly from the Earth's point of view, it looked very rigid, didn't it? It kept its same length at every instant in time, according to the Earthlings. But is it going to be rigid according to the outgoing IRF? Not at all, right? If the right end switches directions before the left end gets the message, the right end starts compressing in towards the left end. And that rod is getting shorter until the left end finally gets the message and turns around. And when it turns around, it's going to end up being much shorter in that case. And there's a good reason to understand that in terms of the length contraction kind of thing. But you can see that what is looking very rigid in one frame is not going to appear rigid in another frame in this particular example. Okay, what about the ingoing shuttle? If we take the point of view of the ingoing shuttle, there's its line of constant time. There are lines of constant time for the ingoing shuttle that pass through the right end and the left end turning around events. And from that one, which event happens first? Well, I have to go out along this axis and say, if I continue these lines of constant time, which one is going to hit the t-axis first? That's going to be the first one to happen. Well, it's going to be this one. So according to the incoming shuttle, the left end switches directions first, which is going to start stretching out that supposedly rigid bar until finally the time comes when the right side has gotten the message and it finally reverses direction. It's going to end up really stretched in that case. We can actually visualize that by drawing this from the point of view of those other frames. I mean, it's hard to see here because I've drawn the world sheet in a way that kind of favors the Earth IRF point of view. If we redraw the diagram, but now I say, well, let's suppose that in the view of the outgoing shuttle, they try to do what the Earthlings did before. They say, well, for us, what we want is when the outgoing shuttle reaches planet X, we want there to be a rigid rod that stretches all the way back and just reaches Earth. And it's going to be trailing behind us the whole time. And we're going to have it turn around simultaneously as seen not by Earthlings, but by us in this outgoing shuttle. Okay, simultaneously means this is a line of simultaneity. This is a line of constant time here. So we want this rod to turn around all at the same time. What would its world sheet look like? That's what its world sheet would look like. Okay, and you can see that it doesn't turn around simultaneously from the Earth's point of view. But in any case, notice that this is a particular time right there. That's one time for the outgoing shuttle. So the whole rod switched directions. Both ends switched directions at the same time, right? And their assessment from that outgoing shuttle frame is that the length of it didn't change. It's behaving rigidly because its length is always going to be this distance along there, and that distance is the same even in this what looks skinny to us here. The way they measure things is the same length there, right? What about in the Earth frame? Well, in the Earth frame, the left end switches directions first, and the right end switches directions later. Do I have that illustrated here? Yes. So here's a line of constant time for Earth. Left end switches directions first, right end switches directions later, and what that means is the Earth is going to say, this is how long the rod is, slicing through parallel to its x direction before anything turns around. Then the left end turns around, it starts stretching, 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 stretching. Finally, the right end at some later time turns around and starts going left. And this is how long it is in the Earth frame afterwards. So it's seen as stretching in the Earth frame. It doesn't look like it's behaving rigidly. No such thing as a classic rigid body in classic rigid body just means it has the same length in every frame if you've made it completely rigid, no matter how you're moving with respect to it and no matter how it is moving. And again, in the incoming frame, this would be how long it is here before any turnaround happens. The events are not simultaneous for the turnarounds. And if we want to envision how long it is after the turnaround, well, it's huge. The slice for the incoming shuttle would say this rod is enormously long after both ends have finally turned around, but they don't turn around simultaneously. It's because they don't turn around simultaneously that it's stretching out, right? One got a head start before the other one got the message. Similarly, okay, so this is getting a little bit tedious, but here's a rod that turns around simultaneously according to the IRF of the incoming shuttle, right? This is a line of their simultaneity. simultaneity. And you can see from their point of view of coming in on the shuttle, it has the same length at every point in time. But from the outgoing shuttle point of view, it's going to be really long at first and then really short. From the Earth point of view, it's going to be pretty long at first and then really short later on. Okay, enough of the twin paradox for now. We'll hear different points of view, I'm hoping, from the group that's presenting on the twin paradox on Monday. Any questions on that before we transition to, I can't remember what Merman calls it. I always call it the pole vaulter and barn paradox. Is that what Merman calls it in the book? There may be a different. It's the same as the garage paradox that we visualize with that car going through the garage with the attendants who are having the argument. I can't, that's just, the book I used when I first learned about this stuff called it the pole vaulter and barn paradox. So someone has a pole vault that's the same rest length as a barn, and then they run relativistically through the barn. There's a front and the back door. It's just like the garage paradox, but you can imagine a relativistic pole vaulter. And let's envision that kind of process, or you can think of it as the garage paradox in space-time diagrams. Pole vaulter is carrying a pole of proper length, 1 light second. Well, that's a huge pole, but let's not worry about that. Runs at high speed, relativistic speeds, through a barn, and the barn also has a rest length of 1 light second. So if you put them next to each other at rest, they would be exactly the same length. We can see that in the diagram here. So here is, the blue is supposed to be the barn's world sheet. So we're viewing this from the point of view where the barn looks at rest and the pole vault looks like it's moving. That's kind of what I would consider a more normal point of view because we're used to standing on Earth. And notice X is measured in light seconds here. So this is a 1 light second barn. X prime is measured in light seconds here. And this is a 1 light second pole vault. So in their own rest frame, even though they're moving with respect to each other, we can see that their rest lengths are the same by carefully reading the diagram, even though the lines look different. Okay, and the question we want to answer is, well, here's the paradox. In the barn's rest frame, that's the horizontal and vertical axes, the pole vault, the pole is length contracted, right? So it's shorter than the barn. And so what we can do is originally have the front door open, the back door closed. When the pole gets in, because it's shrunken, we'll first close the back door. Then after a finite amount of time, we'll close the front door. And then after a finite amount of time, we'll open the back door and we'll be sure that we have enclosed it in the barn. And if the pole vaulter agrees with this, as soon as the pole vaulter starts running at relativistic speeds, he or she is going to be a little bit nervous because from their point of view, it's the barn that's length contracted. Notice here again, from the pole vaulter's point of view, this is the rest length of the pole vault. And that is a line of constant time. So if we want to see how long the barn is, we slice through the barn with a line of constant time. That's the X prime axis. And we can see that it's shorter than the length of the pole vault as measured on the X prime axis. So there's no way that this pole vault is going to fit through the barn. Well, it either is fitting in the barn and it can be enclosed inside, or it isn't. Or we've got some explaining to do. We do have some explaining to do. We've talked about this before, but it's the same idea, just visualized, of the garage paradox. Here's the view of the order of events from the Earth's point of view, right? So this is the pole at any instant in time, right? Instant in time defined by the barn's rest frame. So we're sitting at rest on Earth. Pole vault is length contracted, right? What happens first? The front end enters the front door. As soon as the entire pole is inside the barn, we close the front door. And then a finite amount of time later, we open the back door. And so we're sure it fits in there as long as there's no damage to the barn. And assuming we could open and close the doors fast enough. Okay, how is that possibly going to work from the other frame? And the answer is, well, let's visualize. So conclusion, it's enclosed in the barn for a finite amount of time. How is that going to look from the other point of view? Well, from the other point of view, When we talk about the pole, we're not talking about the same set of space-time points that the Earth was. We're talking about a different collection of events. This is the pole at an instant. This is the pole at another instant. So this is the pole as seen by the person running with the pole at the instant the pole enters the front door of the barn, right? Here's the pole when it reaches the back end of the barn. And here is the pole when the back end of the pole reaches the front door of the barn. But notice the order of the events. The order of the events before was front end entered the front door was first closed, and then the back door opens. But now the order of events is different, right? First, the pole enters the front door of the barn. Before we close the front door, we open the back door, and the pole starts protruding out the back of it. And then finally, we close the front door. So people are disagreeing on the order in which events happened. And this is just a way to visualize that. And if you can take one or two things away from this course and remember them a year from now, or explain them to your grandmother on your Zoom call for Thanksgiving or whatever you're doing, or Aunt Fran and Uncle Fritz when you're talking to them on Zoom eating turkey or whatever you're doing. The fact that if you can remember this paradox and how to resolve it, and the fact that it's resolved by events that are simultaneous in one reference frame or not simultaneous in another, and the order in which events occur can actually switch in certain cases. And that's the key to this. If the back door opens before the front door closes, hey, there's no problem with a long pole fitting through there. It can just protrude out the front before you close, or protrude out the back before you close the front. Okay. And then finally, again, I like to go back to, these are all just perspectives, but there's the same thing happening underneath it all, right? I showed two different perspectives. We could have put more different IRFs axes on there and interpreted what those observers would see. But underneath it all, we kind of want to just keep the idea that this is a view of events that's not biased by one person's point of view or another. In other words, here's the world sheet of the barn in blue. Here's the world sheet of the pole in green. And you might say we bias towards the barn because this one's tilted, but I could have spun the diagram around so that this one was shown vertically and this one was tilted at an angle. I mean, there's no definite direction of up here. So underneath it all, there's something that kind of everyone agrees on. Okay, any questions on those? That was just kind of two paradoxes visualized. And I think it's important to visualize them as well as have the explanations that we might have had before this as well. Okay. One more thing I want to talk about, and I'm not sure this is addressed in Mermin, but it's leading up to something that I want to talk about next week. And that is, let's at least try to visualize. We've been having a one-dimensional space. Everything was happening on the x-axis. I can't visualize three-dimensional space plus 1 dimensions of time. I don't know how to picture a 4-dimensional diagram, but I can try to draw 3 dimensions on a 2-dimensional page just by perspective drawing. So we're going to imagine now that our space is 2-dimensional. So at a certain instant in time, we can move along x and y directions, and I'm showing it in kind of a perspective view where you're viewing it slightly edge on here. So that at some instant in time, that's what space looks like. We're still not in 3-dimensional space, but at least we've got 2 dimensions. And we're going to add our time dimension. Relativists like to have time going vertically for some strange reason. I don't know, that's just always what they do. So our CT axis is going to go up here. So what I've shown down there in blue is space at the time CT equals 0 or T equals 0. Here's space at T equals 1 or CT equals 1. Here's space at CT equals 2. We've got lots of different times, or instances of space corresponding to different times according to whoever's drawing this diagram. This is biased towards a certain person's point of view. And we're not going to worry so much about changing IRFs here, but as much as talking about events in this space. Now let's imagine, this is getting at something that Jessie brought up weeks ago in the philosophy class, a diagram that she was interested in, and I think I said that we would visit it later in the course. Let's imagine At the origin of this person's coordinate system, a light pulse is emitted in all directions. Now, for us, in 3 dimensions, all directions means it goes out in 3-dimensional space, along all spherical directions everywhere away from the origin. In this 2-dimensional world, it means it goes out in all directions. That means every angle around in all 360 degrees. Light will propagate in every direction. So as time goes on, if there's just a very quick propagate everywhere, it's going to move out. It's very short in extent, but it's going to move out at the speed of light. So it's going to propagate away from that point in all directions. So it's going to propagate out further as time goes on, right? We're going to connect up all those circles, and they're going to make up a cone, or at least part of a cone, depends what you mean by a cone. And relative to this event at the origin, we could say the light, the event corresponding to emitting the light. That's a particular event that happens to be at the origin in this coordinate system. People refer to this cone, just the surface of the cone, as the forward light cone of the event at the origin. Forward means forward in time here. Okay? And it tells us something about, well, we're going to sort of map out the space around this. Okay? The interior of this light cone, the inside of it, so it would be like the shape of a solid cone coming to a point down there, is called the future of the event at the cone apex. So we would say relative to this point down there, this interior of the cone is called its future. And there's a reason for that. The reason for that is that if I pick another event up here that's somewhere in the interior of this cone, first of all, if someone were present at that event, they could travel there. They could possibly, because notice traveling at the speed of light means going along this line. So if I'm pointing at a point inside the cone, someone could travel there in principle at less than the speed of light and arrive at it. So you can visit those points, you could potentially be present at them, and you can causally affect something that happens there. So if you're imagining, 3 seconds and however much time this is in the future, something might potentially happen and I want to stop it, I could send a signal that gets there in time, right? If I'm here at this particular event, I could send a signal that has a causal effect on what happens there. I'm not really sure what's going to happen yet, but I could send a signal that says, stop the train, or defuse the bomb, or whatever it is in that situation. Okay, so it's the set of all events that can be causally affected by the event at the apex, and that event doesn't have to be at the origin. I'll show it in other locations, but here I've just happened to put the event in question at the origin. So this is called the future of that event. It's also the set of events that can be visited by someone at the origin, at least if it's in the interior. You couldn't really visit an event that's right on the edge of the cone because you'd have to travel at the speed of light, and you being massive would never get there. There's no method to get up to the speed of light, but you could send a message, I guess, just barely to get to a point on the outside of the cone. Similarly, again, another definition, but it makes sense. We're going to call this the backward light cone of this point at the origin, or more generally at the vertex of this cone. Mathematicians tend to call this whole structure a cone. Both sides of it are part of the same cone. And this is the backward light cone, and it just means, what are all the events such that you could emit a pulse of light and part of that light would arrive just in time at the origin? That's the backward light cone. We don't want to think of light propagating backwards in time, although you could run a movie backwards and, light, but it's like all this light is sort of just, if this is a bit of light here and it's heading towards the origin, it would just barely make it and arrive at that event. It wouldn't arrive too soon or too late. It would just barely make it. So that's the backward light cone. People refer to the interior of that part of the cone as the past of the event at the apex of the cone, okay? It's all of the events that could potentially causally affect what's going on at the origin. So if something's happening at the origin, only these locations in space-time could have potentially causally changed what happened at the origin. And it's also the set of events of things that happened here where someone could travel from that event to the origin and make it, because they wouldn't have to travel the speed of light or faster than the speed of light. Okay. Past and future. Well, the question is, what's the rest of it out here? This may have been in Jesse's diagram. I can't remember. Typically, people call that elsewhere. Elsewhere is, it's not elsewhere, full stop. It's relative to this event that I'm pointing at right here, which happens to be at the origin. It doesn't have to be at the origin, though. Relative to that point, its future is inside the cone up here, its past is inside the cone here, and all the points that are outside that cone, all the way around, are called elsewhere. They're the collection of all events that are neither in the forward or light or backwards, neither in nor on the light cone of the apex event. And more importantly, they're the set of all events that can neither causally affect nor be causally affected by the event at the apex. So if something happens over here, someone dies, even if it's in your, even if it happens at a later time, it's not in what we're going to call your future. If something happens here and you're present at this event, there's nothing you can do about it if we buy the principle of causality that no faster than light signals are possible. Because if if some death happens over here and you want to send a signal that could somehow stop it, the fastest signal goes along this line. You're never going to get over there. It would have to go faster than light. So elsewhere means I can't affect anything that happens over here in the future, and an event down here that is technically at a previous time could not affect what happens to me right here. So, we might be tempted to call a point that's over here and elsewhere in the past, but it's not in the past according to this because it's just sort of unrelated to me whatsoever. I might in the future find out about what happened at that point, but I can't causally affect it. And so those are the three regions that are important to sort of break up space that way in terms of causal effects. And the point of the origin wasn't particularly important. I could refer to the future and the past and elsewhere relative to any event in the space-time, in the space-time that we're talking about. Again, this is a two-dimensional space-time. We can't really visualize a three-dimensional one because light would travel along spheres, and then we'd have to have a continuum of spheres that were getting bigger and bigger as time increased. There's just too many dimensions to show compressed onto a two-dimensional page. Okay. Yeah, I apologize. I'm just talking a lot today, but there's not really a calculational part to what I'm talking about here. It's more like just ways to think about causality. Here's another piece of terminology. This event here at the apex and this event right here, which is inside its future light cone, are called time-like separated events. In other words, they're farther along their distance, if we think of their distance along the CT direction and their distance as measured along in the XY plane or some parallel version of the XY plane up there, they're farther separated in time than they are in space. What that means is I have some hope of getting there. I have plenty of time because I don't have to go that far in space. So they're time-like separated. They're more separated. You can think of this as more separated in time than in space. When things are more separated in time than in space, causal effects can take place, right? If I'm at the first one, I can potentially affect what goes on at the second event by doing something, okay? So time-like separated events are tilted at less than 45 degrees with respect to each other. They've got to have a tilt that's more towards the vertical than the tilt of the edge of the light cone there. Here's another set of time-like separated events. Here's one in the past relative to one at the apex. And I guess I should have said here, I could have drawn those events over here. Here could be one, and then one that is mostly forward and a little bit over would be time-like separated from this event down here. They're just more separated along the time direction. Similar piece of terminology. If light could just barely make it to travel from this event to that event, in other words, you have to travel at the speed of light to make it to this other event, they're called conventionally light-like separated events. And they're just barely in causal contact with each other. In other words, we can get something to just barely get there at the right time, but you wouldn't have time to really react to it because there'd be no time left by the time the signal got to that other one. They're the boundary between the two. And not surprisingly, if the angle is bigger than the angle at which a light beam travels here, in other words, it's more along the spatial direction than along the CT direction, we call those space-like separated events. And those are the events that are, if events are space-like separated, you can ask this question for any pair of events that we draw in anywhere in this diagram. If we point to two events, we could ask, are they space-like separated, time-like separated, or light-like separated? Space-like separated means they can have no causal effect on each other. What happens here at nominally an earlier time can't have any effect on what goes here. Before I go to that, let me just remind you of something we said the other day that relates to this notation. It is exactly events that are space-like separated. Notice, in this IRF that we're viewing this whole diagram from here, this event happens first, and this event happens later. If they're space-like separated, we can switch to a different IRF and make the time order of those two events differ so that this one occurs first and this one occurs later. It's exactly the case where they're space-like separated that we have the ability to switch the order. You could see that if you work through the Lorentz transformations. Why is that important? Well, if things are causally connected and you can switch their order, that sounds like there could be some confusing consequences. The effect becomes the cause and the cause becomes the effect, and at least that's going to cause a lot of cognitive dissonance in what you're thinking about. So in this particular case, it's exactly when any events that are space-like separated can be switched in their time order by switching to a different reference frame and viewing their time coordinates in that other reference frame. If things are time-like separated, like this pair, here's one, this is supposed to be inside, not on the edge of the cone, but inside the cone, right there. If they're time-like separated, you can't switch their time order. You can switch their space order, which isn't that amazing, right? I could say one happened here in my reference frame and another one happened later at this point over here. Well, but just by zooming in that direction, I might be able to see the later one that happened behind me, whereas it was in front of the other one before. That could happen for Newton too, so that doesn't sound as amazing. But time-like things, you can switch their spatial order, but you can't switch their time order. Space-like separated, you can switch their time order, but you can't switch their space order. So there's a certain symmetry between the two. Okay. And finally, I just thought I'd mention for three-dimensional kind of diagrams, in those cases, light doesn't expand along a circle, it expands in spheres. We would need a 4D diagram to deal with it, and Merman makes the comment, I think, towards the end of the chapter. If you're stuck in this situation where you have an inherently three-dimensional spatial problem and you want to envision what's going on in 4 dimensions, either maybe there's some way to reduce it down to something that's analogous in 1 dimensions or 2 dimensions. Often that's the case. If the relative motion is all along one direction, make that direction your x-axis, and maybe you can get away with a 2-dimensional space-time diagram. Or forget about visualizing and just crank it through with the Lorentz transformations where you don't really have to have any intuition. You just turn the crank, plug it in, and interpret the results. Okay. I think since I've been talking so much, I'll ask for any questions first, and then maybe we'll quit a little bit early today just so I don't keep yammering on for another 15 minutes. And that's because we're starting now the last bit of material, which is going to be loosely based, well, there's going to be some material that doesn't fit in anywhere in Merman's book, and then a transition to the E equals mc squared kind of ideas. And so we'll try to do that on 2 days or 3 days next week. It depends. Any questions? We're through with chapter 17 now, so you're ready to finish up that, start and finish that chapter 17 homework over the weekend. Of course, it's relevant for our exam on Wednesday, which covers predominantly 13, 14, and 17, because those are the things we had the big homework assignments on. So try it over the weekend. We can work through the kinks Monday and Tuesday in office hours or whatever, and we'll start talking about something new on Tuesday, which will not be covered on Wednesday's exam. Silence. That's okay. All right. I will see you guys in class this afternoon.